Can we find about the function anything from the function about the function itself? No. Just limits, x and y intercepts, there is nothing else. What do you think the next step would be? Yes. Let's continue with the first derivative, of course. Not a big deal, right, in this case. Careful, we need to differentiate this. Not the one under the equation or anything like that. We go back to the original function. So negative 6x squared plus 6x plus 36. Do you agree with the first derivative as being negative 6x squared plus 6x plus 36? Yes? What do we need next? If the function has, how are they called? We're looking for now critical numbers. Critical numbers, if you remember, they come from two sources. One from f prime being 0 and the other one from f prime being undefined. But this is a polynomial function. Can it be undefined, the derivative? No. So only from f prime of x equals 0. Negative 6x squared plus 6x plus 36 equals 0. Yes, I will divide both sides by negative 6 and get x squared minus x minus 6 equals 0. I will factor to find the solutions. Any questions so far? Any questions so far? So then x minus 3 and x plus 2. So x equals 3 and x equals negative 2 are the critical numbers of this function. We have to go back and put them in the table. So negative 2 and 3, kind of tight here. I have to determine the corresponding y values. In the original function, I have to plug in negative 2 and get this value. And I have to plug in 3 and get this y value. So back to y equals, clear. And I plug in negative 2, x cubed, and then plus 3x squared. And then plus 36x, yes. Okay. Second in table, and I want negative 2 and 3. At negative 2 is negative 44. And at 3 it's 81. I write those values in the table. The next step, I have to find the sign, study the sign of the first derivative. Let's look at the first derivative one more time. So here's the first derivative. This is the first derivative. It's 0 at negative 2 and 3. It's 0 at negative 2 and 3. Between negative 2 and 3, is it positive or negative? Plug in 0 if you don't want to think in terms of this. Plug in 0. Plug in 0, please. Chris, plug in 0. Positive, very good. That's all we need to know. So in between negative 2 and 3 is positive. It's guaranteed, it's quadratic. It can never change signs more than twice. So now this is the moment of truth. Right here, right now. That's how I catch my mistakes. If these two rows do not work well together, I have to start from scratch. Ready to check? Okay. From positive infinity to 0, what does the function do? Decreases. Is that supported by the sign of the first derivative?
Yes.
From 0 to negative 44, what does the function do? decrease. Is that supported by the sign of the first derivative? From negative 44 to 0, what does the function do? Is that supported by the sign of the first derivative for that interval? Between 0 and 81, the function is increasing. Is the first derivative supporting that? From 81 to 0, it's decreasing. Is the first derivative, the sign of the first derivative, is that cooperating? And then from 0 to negative infinity, is the function decreasing? Yes. Is the first derivative negative? This is when I know that the first two rows work well together. And we have just used the first derivative test. Let's write it. We used it without knowing what it was. So the first derivative test. So let's write here, because we haven't finished. One more second. Negative, 0, positive. What type of point is negative 2, comma, negative 44? We don't know absolute till we graph it, and it's a cubic function. It cannot have an absolute. So negative 2, comma, negative 4, because of the sequence of signs and that because the derivative is 0, it's a local min. Good. The change of signs between 0 and negative, and the first derivative is 0, and 3, comma, 81 will be a local max. Okay. So here's the first derivative test. If C is a critical number of a function, if C is a critical number of a function and the derivative changes sign from positive to negative, that results in the local max. From negative to positive, that results in a local min. And nothing if it does not change sign. Also, I would like to write that when the first derivative is positive, please tell me what the function is doing. When the first derivative is negative, please tell me what the function is doing. So we write that together. Okay, so if C is a critical number of a function and the derivative changes sign like we did, we already talked about that last week, from positive to negative, that results in the local max. From negative to positive, that results in a local min. And if it does not change sign, that is not a local max or local min. So when the first derivative is positive, what does the function do one more time? The function is, when the first derivative is positive, let's look here. Yes, it's increasing. And when the first derivative is negative, what does the function do? Decreases. And this is the first derivative test. So that is a local min, and 3, comma, 81 is a local max. There is nothing else we can learn about the function from its derivative, from studying the derivative. So let's take a look at one more thing. Can I say now that between negative infinity and negative 2, this function is decreasing? Union between 3 and infinity? Yes. Can I say that the function is increasing between negative 2 and 3? These are the intervals of increasing and intervals of decreasing. So the function is decreasing between negative infinity and negative 2, union between 3 and infinity. I'm going to put that in writing also. And it's increasing between negative 2 and 3. Do not use closed intervals. So we also learn, you don't have to write that on the side because I already see it if you put it in the table. But the question in WebAssign may ask you. So we will say for our function f is increasing on the interval negative infinity, negative 2, union 3 to infinity, and the function, I meant the other way, of course, and the function is increasing on the interval negative 2, 3. Sorry about that. Got carried away. So the function, of course, is decreasing between negative infinity and negative 2, union 3 to infinity, and it's increasing between negative 2 and 3. We exhausted the first derivative. We can't learn anything about the function from the first derivative. Just increasing, decreasing intervals, critical numbers, max, min. We're done. What do you think is the next step? And of course, the next step is the second derivative. Well done. Eddie, you wanted to ask something? Please.
No, you answered it. I was wondering what the first derivative was going to show us all, but
Yes, that's it. It shows increasing, decreasing intervals and max, min. If any. Okay, so now let's study the second derivative and see what we discover using the second derivative. Okay, so the second derivative, we'll go back to the first, like 5 pages earlier. This is the first example, that's why it's so long. So here's our first derivative. So the second derivative would be negative 12x plus 12. And negative 12x plus 12. We are going to set it equal to 0. Negative 12x plus 12. And no, we are not going to find max min. No. Was it 6? What did I do? It is 6. Thank you. Thank you. With your permission, I'll start another page so I don't waste your time. So it was negative 12x. Where did I look? I trust you anyway. Yes, negative. Yeah, it was negative 12x plus 6. Yes, of course. Okay, so we set it equal to 0, and we get negative 12x plus 6 equals 0, or x equals 1/2. Would you agree? Okay. Question. What do we learn from the second derivative about the function? Here's what we learn. Concavity. If the function opens upward, or if it opens downward. Here's an example for you, x cubed. X cubed does this, right? Does this function ever turn? One more time. If my hand never decreases or always goes up, it can never have a turn. Right? What happens here at this point? It changes concavity. From opening downward to opening upward. That point is called a point of inflection. So this can become a point, the x-coordinate, point of inflection only if the second derivative does what? Changes sign. Only if the second derivative changes sign. So, yes, I kind of extended myself, but I have to insert 1/2 and put 0. If it's too congested, I'm more than willing to create the table one more time. So 1/2, as you know, we know it's between 0 and 3, so the second derivative is 0. Now we study the sign of the second derivative. Here it is, a linear function with a negative slope. A linear function with negative slope. It comes from and goes where?
positive.
Of course, we know that. So from positive to negative. When the second derivative is positive, the function opens upward. When the second derivative is negative, the function opens downward. So before I forget, I just want to write here first derivative and second derivative. What we learned what we normally learn from them about the function. Increasing, decreasing, intervals, max min. From the second derivative we learn concavity, opening upward or opening downward, an inflection point or points. So the first derivative gives us increasing, decreasing intervals. It tells us max min if it changes sign, and of course critical numbers without which max min don't exist. The second derivative, it tells us the concavity, if we say the function holds water or it does not. And the inflection point where the concavity changes, that's an inflection point. Okay, so obviously I have one more number to insert right here. I have to plug in 1/2 in the function. So we go to our calculator. Since I already have that, I'm going to plug in 0.5. I have the function in there. I get 18.5. So this is 18.5. 1/2 comma 18.5 will be the inflection point. So this is what is called the IP. 1/2 comma 18.5 will be the inflection point. Okay. Given all this information, we're able to graph this function without the use of the graphing calculator, which we were not ever able to do before. Ready? I don't care for any calculations, nothing matters anymore except the table. And let's start. There are absolutely no more secrets. So this was page 10. About this function. Okay. I will plot the points first. To the best of my abilities, I'm going to create a scale that makes some sense. So at negative 3.6, 1, 2, 3, 4, and negative 3.6 is 0. At 0 is 0. And at 5.1, 1, 2, 3, 4, 5.1. Now it's going to be a little bit difficult, the negative 44, the positive 81, and the 18.5. So I'm going to choose a scale of 10 for the y-axis. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5. So this will be negative 44, and this will be 81. This is just a scale. And 10, 20, so it's going to be this 18.5. So please follow me for a moment, and then I'll do it again with you if you'd like. So here's what I do. The function is coming from positive infinity. So I'm going to say positive infinity. Yes, x approaches negative infinity. The function approaches positive infinity. It's decreasing, opening up till this point. Decreasing, opening up till this point. Opening up, decreasing. Okay. It will continue to negative 2 comma negative 44. Negative 2 comma negative 44 is this point. So it will continue. I'm going to have to make some adjustments. So it will continue to this point where it turns. Because that is a local minimum, where it starts increasing to the origin, still opening up, but this time increasing to 0, 0. Then it goes to 1/2 18.5, which is this point here, still opening upward. where it changes concavity, because at this point, that's the inflection point, it continues to open from now on, it opens downward, increasing to 381. Oops, I should have put my points first. Increasing to 381, comes down to cross the x-axis at 5.1, and going towards negative infinity. It's a polynomial function, smooth, continuous, should not have any corner cusps, etc. So this is the function f of x. It was negative 2x cubed plus 3x squared plus 36x. But this was not possible in the previous courses because we did not know anything about the first derivative, the second derivative, and what they say about the function. Yes, Eddie, please.
Is this the same way as how you were graphing like multiplicity?
The way I graph what?
How we were taught earlier to graph with by using the multiplicity.
In the pre-calc? Yes. However, the multiplicities will only give us the x-intercepts and what happens at the x-intercepts.
Okay.
If a multiplicity is even, the function turns. If the multiplicity is odd, the function crosses, either slowly or fast.
Okay.
Yes. But that is the only thing that we learn from multiplicities, only what happens on the x-axis. But in pre-calculus, we had to determine these points, the max-min, using the calculator. We did not know anything about the first and the second derivative. Any questions about this? There is also something called the second derivative test, which I personally never use, but I need to talk to you about it. And you decide whether you want to use it or not. I don't have anything against it, but I don't use it. So the second derivative test says this. You find the critical numbers, you put them in the table, in organized manner, and you do not study the sign of the first derivative. The reason I do is because I want to make sure that these two, and I don't have an error. That's what I check, whether these two rows go well together or they are in sync. But the book says, as a second derivative test, you are not determining the sign of the derivative. Don't waste your time with that. You will be able to determine the sign of the first derivative from the sign of the second derivative. But if I have an error in the first, I'll carry the error to the second. So that's what I'm worried about. And then how do you find the max-min? If I don't study the sign of the first derivative, I don't know where the max-min are. Here's how I know. So there is a critical number at -2. How do I know whether it's a max or a min? Look at the second derivative. What could it be? Of course. So you can go and fill in the negative and the positive right away. But you have to wait till the second derivative to be able to do that. I don't want to wait. So now here's another critical number, 3 comma 0 is right here, where the second derivative is negative. What could that be? Yeah. But if again, it's not that I don't trust myself, but we know, mistakes happen. So now you can fill in, since this opens up and this is a critical number, the sequence must be negative positive. If this is a critical number and right in that territory, the second derivative is negative, the signs must be positive negative, because that has to be a max, local max. And that's what the second derivative test is telling us. So let's write it down. You can use it if you'd like. I will not test you on it, because I'm not using it. I don't think it's that useful. In certain situations, maybe for some functions it may. So second derivative test. The second derivative test. F prime of c is 0 or undefined. And the second derivative is positive. What does that mean? C is A, and the second option, f prime of C is 0 or undefined. And f double prime of X is 0. That means that C is A. And you'll tell me what? One more time. So f prime of C is 0, like we had f of 2 was 0 or f of 3 was 0. Undefined, and the second derivative is positive. What point is that? C gives a minimum. C gives a minimum, or is a min, local min. If C is a critical number, in other words, that's what I'm saying with this. C is a critical number. If C is a critical number and the second derivative is less than 0, what does that mean? C is a local max. That's the second derivative test. And now, since we already talked about the second derivative, now this kind of makes more sense, but how I will graph it, I'll have to, so it's concave up on this, and then whatever they did here, God knows, concave down on this, and then the result was concave up on this, and so on and so forth. But there is no information. It's just all listed. Now put this together and come up with this graph, which I think is difficult. Okay, I know we have 7 minutes left. Would you like to at least start another problem? The first one was long because I had to explain what the first derivative test, what the second derivative test is, what we learned from the first, what we learned from the second. Would you like at least to start another problem?
Yeah. Yes.
Okay, so let's start, and I promise I'll stop in exactly 6 minutes, and we'll continue it next time. So let's start with, let's continue with another easy situation, I think. Just a simple rational function. So let's say you give me a simple rational function. I don't know, 2x minus 4 over x plus 1?
Yeah.
Okay, very good. Get the table going right away. I do not take credit for the table. It's not my invention. Okay, domain first. Careful, negative infinity to. Very good. 0 has to be in the table, always. Even if the functions are undefined there, 0 has to be in the table. Good. Now, this function is rational. It's undefined at -1. I have to determine this, the limit. This on the left-hand side of -1. This on the right-hand side of -1, 0, and that limit. And also when the numerator is 0. Where does this cross the x-axis? At 2. What happens at 0? Y value is negative. Can anyone give us these limits? And then we can say we exhausted the function. We can't learn anything from the function anymore. What is the limit as x approaches -infinity? We can use L'Hopital's rule now. The derivative is the denominator. The derivative of the denominator is
1.
What is the horizontal asymptote then?
2.
Very good. Good. The limit on the left and limit on the right, we know that x equals -1 must be what? For sure. x equals -1 will be guaranteed. Very good, a vertical asymptote. And these must be infinities. That's why we study those limits at the very beginning. So from the left with -1.1, where does that go? The numerator goes to negative, the denominator goes to negative. So then that left-hand side goes to
Negative.
So with -1.1, negative, negative, positive. With -0.9, negative, but the denominator this time is good. This is it. We're done. There's nothing else I can learn about the function. One more time. What did I learn? Limits for the end behavior, limits left and right of the vertical asymptote, the x-intercept, and the y-intercept. There's nothing else. Now I will differentiate the function. And then if we have time, we'll study this sign. If not, we'll stop. F prime of x. The top prime.
2.
Very good. Times x plus 1 minus the top. Don't forget parentheses. Times 1. So this is 2x plus 2 minus 2x plus 4 over x plus 1 squared. Very nice. 6 over x plus 1 squared. What does this say about the function? Exactly, which means that the function is always, thank you. The function is always increasing. No critical numbers. The derivative is undefined at -1, but so is the function. No critical numbers coming from f prime being undefined. And this expression, f prime of x of 6 over x plus 1 squared, is never 0. Never 0. Good. So we'll stop after we make these two work, if they work. From 2 to infinity, what does the function do? Is that supported by the sign of the first derivative?
Yeah.
Perfect. From -infinity to -4,
Increase.
is that supported by the sign of the first derivative?
Yes.
From -4 to 0, what does the function do?
Increase.
Very good. Is that supported by the sign of the first derivative? And from 0 to 2? Very good. So next time we're going to determine the second derivative and graph the function. Yes?